Differentiation rules. Theorem. Suppose u and v are differentiable vector functions, c is a scalar, and f is a real valued function. Then the following rules hold true. The derivative of the sum of two vector functions is equal to the sum of the derivatives. 2. The derivative of a scalar multiple of the vector function u is equal to the scalar multiple of the derivative of u. The derivative of f of t times u of t equals f prime of t times u of t plus f of t times u prime of t. This is similar to a product rule, now applied to the product of a scalar function and a vector function. Similarly, the derivative of u of t dot v of t is equal to u prime of t dot v of t plus u of t dot v prime of t. Five. The derivative of u of t cross v of t is equal to u prime of t cross v of t plus u of t cross v of t. And 6, the derivative of the vector function u of the scalar function f equals to u prime of f of t times f prime of t. This rule is called the chain rule, applied to a vector function of a scalar function. The rules 4 and 5 are collectively called the product rule for the dot product and cross product cases. In the rule 4, since dot product commute, the order doesn't matter. But in 5, since cross product doesn't commute, meaning u cross v is not same as v cross u, so we have to maintain the order. U prime cross v, and in the second term, u cross v prime. Here we can commute these two terms, but we cannot commute the appearance of the vectors in each term. For example, we cannot write v of t cross u prime in the first term. To prove these rules, we need to consider the vectors u and v with components shown here, where each u function and v function are differentiable. Now we have u of t plus v of t equals the vector whose first component is the sum of the first components of u and v, and the second component is the sum of the second components of u and v. Similarly, the third component is the sum of the third components of the vector functions u and v. Since u prime and v prime exist by the hypothesis, by applying the theorem 4.2.1, we have the derivative of u plus v is the derivative of this vector, and when we apply the theorem, the vector, which is obtained by just replacing the first component by the derivative of the first component, and the second component is replaced by the derivative of the second component, and the third component is obtained by replacing the derivative of the third component. Now, for the scalar functions, the derivative of sum of two functions is exactly equal to the sum of their derivatives, so as in the cases of the second and third component. Now we can write this vector as a sum of two vectors. The first vector has components u1 prime, u2 prime, and u3 prime. and the second vector has components v1 prime, v2 prime, and v3 prime. The first vector we see is exactly the derivative of the vector function u, and the second vector here is exactly the derivative of the vector function v. So we proved the derivative of the sum of two vector functions equals to the sum of their derivative. This concludes the proof of 1. To prove the statement 4, we have the dot product of two vector functions u and v as shown here. Instead of writing 3 terms, we would like to use the summation symbol. Since u prime and v prime exist, by applying the theorem 4.2.1, we get the derivative of the dot product of u and v as the derivative of the sum of the products of the component functions. Now, for the scalar functions, the derivative of the sum is the sum of the derivatives, which gives this step. Now, by applying the product rule in the case of the scalar functions, we get this step. And then splitting the summation over these two terms, we would get the next step. Now we observe that the first term here is simply the dot product of the vectors u prime and v, and the second term here is also the dot product of the vectors u and v prime. This concludes the proof of the statement 4. Let's have a look at an example of the application of these product rules. If R is a vector which has a constant magnitude c, then R prime of t, the vector, is orthogonal to the vector R of t for all t. Let's look at the proof of this statement. We have, from the previous theorem, the derivative of the dot product, which can be written as R prime of t dot R of t plus R of t dot R prime of t. Now the second term here can be rewritten as this term, since dot product commutes. Then we have two similar terms, R prime of t dot R of t plus R prime of t dot R of t, which can be put into a single expression as follows: 2 times R prime dot R of t. Whereas in the left hand side we have the derivative of the dot product of the vector R of t with itself. But R of t dot R of t equals the square of the magnitude of the vector R, which is equal to c squared as the hypothesis. Then the equation 1 gives the right hand side is put into the left hand side here, and the left hand side here is replaced by the derivative of c squared, which is simply 0. And then we divide the equation by the factor 2. Since the dot product of these two vectors R prime and R equals 0, this proves that the vectors R prime and R are perpendicular to each other or orthogonal to each other for all value of t. Geometrically, this result says that if a curve lies on a sphere with the center at the origin, then the tangent vector R prime is always perpendicular to the position vector R, as shown in the figure.